Welcome, ladies and gentlemen, to our second lecture on waves, and this time we're going to concentrate on longitudinal waves, and in particular, we're going to look at sound. So recall that longitudinal waves are waves where the oscillation of particles is in the same direction as the velocity, as the wave velocity. So if we have a wave moving this way, and we have some, say, particles of air, our little particle of air oscillates. It doesn't move with the wave for the whole distance, but it oscillates back and forth like this in the same kind of unit vector direction as the wave. Okay, and so this particle moves along, and it bumps into another particle and causes it to oscillate. Let's put it here. Bumps into this guy, right, and this guy then oscillates, right, and that goes along down the line, and what we end up with are areas of much higher density or much higher pressure, some areas with less, and areas of higher pressure again. Okay? Now I've drawn it very binary, but of course this is all much more continuous, right? It's very dense here, and then it goes gradually less dense as it goes this way. It reaches some point where it's the lowest pressure, okay? And then it goes back up until it reaches this point where it's the highest pressure again, okay? And this structure here, this is just like the crests and troughs of our transverse wave, okay? Our wave on a string or something like that. And so if we have multiple sources of these longitudinal waves, they obey superposition just like the waves on the string, okay? So y total is, again, if we have two waves, it's the sum of the two wave functions, okay? And this constructive and destructive interference can allow us to create situations of standing waves in columns of a fluid as well, okay? Much like creating standing waves on a string that's fixed at both ends, if we have a column of a fluid, usually air, we can create standing waves in that as well, okay? So a sound wave is just this kind of longitudinal wave that we were just describing, okay? And it's what I'm going to call a pressure wave from now on because it creates areas of high and low pressure, all right? And for us, that's usually in air, right? We usually hear sound through the air. You're hearing sound that a microphone is picking up from me right now because my voice is creating a pressure wave in the air, okay? But it can work in any medium. It doesn't have to be in air. And the wave function for these waves is just like for the waves on a string. So for a wave traveling in the plus x direction, we have y xt equals a cosine kx minus omega t. But the difference here is that y is in the same direction as x, okay? So x is going to be the equilibrium position of a particle, and then y is going to describe this oscillation back and forth as the wave goes this way, all right? So that's v, and that's x hat, because this function that I wrote here is for a wave in the positive direction, right? Remember, for a negative, we would make this plus, right? That's for a wave traveling in the negative x hat. This is for a wave traveling in the positive x hat, okay? So x is this position of equilibrium, and then at every point along the area that the wave is traveling through, we can use x to describe the equilibrium position of the particles in that direction, right? And then y to describe the oscillation of those particles around the equilibrium. Okay. Now this is exactly what we were doing with the transverse wave as well, right? X was the point of equilibrium, and y was the oscillation around that equilibrium. The difference was just that the way that they were aligned, right? In the transverse wave, it was like this, so it made a lot of sense to call it x and y. Now, we still call it y just because we already were calling it y for the transverse wave, but they're in the same direction, but we can describe the point by taking x plus this, right? Plus this oscillation. So like we said before, the jostling back and forth of these particles causes these high and low pressure areas, right? That's why I call it a pressure wave. And so when your ear or microphone or something senses sound, what it actually senses is pressure differentials. Okay, so you have an eardrum, and behind the eardrum is this column of air that has a little something connecting it to the outside world. Okay, so you have atmospheric pressure in here. Okay, and then you have your ear going out this way. And what happens is these pressure waves come in. Okay, so we have the dense, and then the lower pressure, the higher pressure, right? And these pressure waves come in. And what happens is, right here next to the eardrum, the pressure goes up and down, right? And the pressure in here is always atmospheric pressure, and that's the pressure that this part out here is oscillating around, right? It's getting more and less dense compared to atmospheric pressure. So as the pressure goes up and down on the outside of the eardrum, it means that there's forces pushing on the eardrum like this, okay? You always have atmospheric pressure pushing out, and then pushing in, we have this varying pressure, okay? And so what we end up with is basically a force that either presses in or out, the net force of the pressures on either side. And so your eardrum vibrates, okay? And your brain can interpret that vibration as sound, okay? As you pick up the frequency, and that's different pitches of sound. So in many ways, in particular for humans, the pressure wave quality of sound is much more important than the particle displacement picture, okay? But we have to understand that the pressure wave part comes from the fact that the particles are displaced, okay? That's how the pressure wave is made, is the oscillation of the particles. And so this wave function up here that I wrote earlier, this thing was for the particle displacement, right? But we could also express the wave function as the pressure wave. And then the wave function can be a pressure function instead, right? And so we write for the pressure function, P of x and t is equal to BKA sine kx minus omega t. Okay? Now, this BKA, this ends up being the amplitude, right? Whenever we have these constants out in front of our sine or cosine function with these wave functions, that's the amplitude of our wave. P max is equal to BKA. Okay? And this P max is what dictates the loudness of a sound. Okay? So different listeners will perceive different pressures as loud or not loud, but the loudness is always tied to this max pressure. Okay? And this B is the bulk modulus of air, okay? Or of whatever medium the sound is traveling through. And a bulk modulus is just kind of an object's resistance to being compressed, okay? And so it's just a constant. We go out and we measure it for different materials, and we measure it for things like air and water and things like that. And then we have this bulk modulus that describes how much the medium resists being compressed. And then we have K, and that's the wave number, and then we have A, okay? And A was the same A here. It's the maximum displacement of the particles. So most sounds that we hear have a much more complex wave than the sine wave that we've outlined here, okay? And this is because most sounds are a combination of many frequencies. And each one of these frequencies would have a nice sine wave like what we've drawn here, okay? But then when we have all these frequencies traveling through the same air together, we get some conglomerate wave that's combined by superposition, right? Y total equals Y1 plus Y2 plus et cetera, okay? So for a given frequency, we would have just this nice sine wave. In practice, sound that we hear doesn't usually have this nice sine wave shape because it's so many frequencies mixed together, okay? And then when we add them all together in superposition, we get some monster wave that's doesn't look anything like this nice perfect sine wave, okay? So let's talk for a second about the speed of a sound wave. And the speed of sound can be calculated by looking at the bulk modulus, which we said was the resistance to the medium to being compressed, right? And the density of the medium. So the speed of sound in a fluid is V equals B over rho in a root, okay? The bulk modulus divided by the density. So when a medium resists compression more, the speed of sound increases, right? And when the medium is more dense, the speed of sound is slowed down, right? So in practice, at the temperatures and pressures that we're usually dealing with on the surface of the Earth, liquids are generally much more incompressible than gases, right? Liquids can barely be compressed at all. And they're also more dense, but most of the time the change in compressibility is larger than the change in density, okay? So in general, now this is not always true, okay? But in general, the speed of sound is faster in liquids than it is in gases, okay? At the kind of temperatures and pressures that we deal with on the surface of the Earth, and for kind of average stuff. So for air, I know off the top of my head that V equals 344 meters per second, okay? For air that's about 20 degrees Celsius, which is kind of just your standard normal air that is always used, okay? It's your kind of unperturbed standard for air. 20 degrees Celsius is, you know, they call it room temperature. It's a room that's a little on the warm side, I think, but that's just kind of a standard speed for air, right? And then in water, at the same temperature, now this one I don't know as well, but I think it's more like 1,500 meters per second, okay? This one I know off the top of my head. That one is exactly right. This one is, I'm in the ballpark, okay? It's probably not exactly right, but it's around 1,500 meters per second. So you can get an idea of the difference in speed between the two, right? Now, if liquid was truly incompressible, then the speed of sound in a liquid would be infinite, right? Because if it was truly incompressible, then if I move this particle at all in this way, then the particle right next to it has to move the same amount that way, right? Does that make sense? Because if the particles get any closer together, then it's compressible, right? So if it was truly incompressible, the particles would all have to push on each other at the same time, and I would have an infinite speed, or the speed of light, which is not infinite, but it's kind of the speed limit of the universe, okay? And I suspect if this were the case, we would run into some relativistic effects where this would still be limited by the speed of light, okay? But in any case, that's not what we have, okay? So we don't have this situation, and sound isn't transmitted instantly in water. And that's one of the ways that we can know that even though a liquid seems almost completely incompressible, it's not incompressible, okay? It can be compressed a tiny amount, but only a little bit, okay? It's, in effective sense, often can be treated as incompressible, but it's not truly, in the most technical sense, incompressible, okay? So that was an aside. We have that velocity is the bulk modulus divided by the density, okay? But the truth is, the speed of sound in a gas depends a lot on the temperature of the gas, okay? So this is a very rough picture, and if we have a given temperature, then we can use the bulk modulus and the density, okay? But actually, the speed of sound in a gas can be a little bit more precisely expressed with this equation here, okay? Gamma RT over M and a root, okay? And so what is all this stuff? All right? First off, you see that our velocity is now a function of temperature. Okay, so this is a much more realistic picture for a gas because the speed of sound does tend to depend greatly on the temperature of the gas. Okay, so gamma is a ratio of heat capacities. Okay, and we're not going to get too much into that because we're not going to cover thermodynamics in this class, and so it's not really going to come up. But a heat capacity is basically a material's ability to take on heat, okay, to be heated. And there's two ratios for this. There's constant pressure and constant volume, and the ratio of this is what makes gamma, okay? And so I'm going to give you guys the values of these things for atmospheric air, okay? For atmospheric air, this is 1.4, and that's an exact number that we're going to use, okay? So the exact number then is 7/5, okay? So this one, as far as we're concerned, sig figs goes out to infinity, okay? Infinity sig figs. It's exactly 1.4. Now, for atmospheric air, it's not exactly 1.4, but the way that they come up with this 1.4 makes it so for our purposes, it is exactly 1.4, okay? M is the molar mass of the gas. So for atmospheric air, okay, again, for atmospheric air, it's 28.8 times 10 to the minus 3 kilograms per mole, okay? And a mole is just a certain number of molecules. It's Avogadro's number of molecules. I'm not going to get into that, okay? That's for chemistry. If you take a chemistry class, you probably heard moles tossed around all the time, okay? This comes more from chemistry. This mole is a certain number of molecules, okay? But this is the molar mass, so it's how many kilograms air weighs when you have a mole of those molecules, okay? R is a constant for all gases, okay? So this one isn't just for air. This is for all gases. But again, then for air, because it's a gas, it's 8.314. And this goes out much further, okay? I'm just going to stop here at 4 significant figures. And it's joules per mole Kelvin, okay? And so now notice, R here, I've given you a constant, and it's in terms of joules per mole Kelvin. And we know in this class, because we do unit analysis all the time, we're very keen to these kinds of things, right? We're very keen to what units things have. And so that tells me immediately the temperature in this equation, if the units are going to work out, well, it must be in Kelvin, right? So T must be in Kelvin in this equation, okay? And to put temperature in Kelvin, we just take, so we'll do T sub K. Temperature in Kelvin is equal to temperature in Celsius, okay, plus 273.15, okay? And that puts it in Kelvin. Now, in Celsius, of course, it's 20 degrees, right? It'd be 20 degrees Celsius. In Kelvin, the degrees just go away, okay? In Kelvin, it's just 273.15 Kelvin. Not degrees Kelvin, just Kelvin. And that gives us understanding that temperature must be in Kelvin, okay? So we know we have to convert that. And then we have these other 3 variables, all for atmospheric air. This gives us a really nice way now to figure out the speed of sound in atmospheric air, okay? Now, if I get a gamma and an m for any other gas, I can also use this same equation, okay? But the gamma and the m that I'm giving you right now sets you up to find the speed of sound in any atmospheric air, okay? So now let's talk about intensity, okay? Intensity is going to be the loudness of the wave. It's related to Pmax, okay? And it comes from the amplitude of displacement of the particles. Okay, the bigger the amplitude of displacement on the oscillating particles, the greater pressures that we get in our changing pressure. Okay, and we can represent this intensity using the speed of sound. Okay, so the intensity of a sound wave is equal to P max squared over 2 rho v. Okay, where v is the speed of sound and rho is the density of the gas. Okay, and like I said, the intensity is related directly to the loudness of the sound, right? But intensity is also inversely related to the distance from the source. So intensity, of course, is related to P max. And so it goes like P max over R squared, where R is the distance from the source. Okay? And there's some other constants in there and stuff. That's why I wrote goes like here instead of equals. Okay? But we're going to skip that. It goes like this pressure over R squared. Okay? And so the intensity of sound is decreasing as we move away from the source. And it's decreasing as this 1 over R squared, right? So if we know the intensity at one spot, we can find the intensity in some other spot with the formula I1 over I2 equals R2 over R1, and that quantity squared, okay? So the R2 and the R1 are both squared, right? As they must be. If I square one of them, I have to square both because there's no units on either side of this equation, right? So this allows us to find the intensity at any given point if we know the intensity at one point, okay? If we know the intensity and the distance. So you might have, say, a speaker and it's putting sound out in a cone like this, and we know the intensity here, and we know this distance. So we know R1, I1. And then we say, okay, but at R2, what is I2, right? And this formula right here allows us to find I2 out here at this distance, R2. Okay? So we also have kind of a standard scale for describing the loudness of something, and that scale is called the decibel scale. And the decibel scale relates the intensity of a sound to a reference intensity. So the formula for calculating sound intensity in decibels is D equals, I'm going to say C here, okay? Log I over I naught, okay? And in this, C is equal to 10 decibels, okay? Little d, capital B is a decibel. And I naught, that's our reference intensity, right? So the whole thing is we're going to compare it to a reference intensity. And that reference intensity is 10 to the minus 12 watts per meter squared, okay? So this is our decibel, okay? It's our decibel system. So notice if I have some intensity, right? If I'm given an intensity, I have to make sure it's in units of watts per meter squared because that's what I know I naught in, okay? And I can't have units inside of a log. And this one, notice I wrote log and not natural log, right? I wrote log. I didn't write ln, natural log, okay? Log, this one is base 10, okay? You can have a log in any base, but generally the ones you see are natural log, which is in base E, and log, this normal log, which is in base 10, okay? This log is a base 10 log, not a natural log. So now let's move on to interference. The pressure waves that make up sound can have constructive and destructive interference in the very same way that we discussed in the last lecture, okay? So you can imagine if I have two waves and I have my high pressure region, my lower pressure region, my higher pressure region, right? Then imagine I have another one that's a lower pressure, oh, that's kind of higher. A lower pressure region like this, a higher pressure region in here, lower pressure out here again. So this one looks like trough, crest, trough, okay? And this one looks like crest, trough, crest, okay? And you can see these are opposite, and these are going to combine with superposition and give me no wave, okay? If they're in the same phase, if they have the same amplitude, right? All the same requirements hold from our transverse wave example, okay? So if these things have the same frequency and they have the same amplitude and they're just 180 degrees out of phase, what I get in the end is no wave, okay? And so what I get in the pressure wave sense is just atmospheric pressure, okay? Undisturbed atmospheric pressure. Assuming we're in air, right? If we were in water or something, we'd have the undisturbed water pressure, that kind of thing, okay? Essentially, I get no pressure wave. If, again, same frequency, same amplitude, 180 degrees out of phase, okay? Any other combination, I still just add by superposition, but I won't get no wave unless I have this very perfect interference, right? And this is actually how active noise canceling works, okay? So if you've ever had a nice set of headphones that incorporate active noise canceling, you probably know that you put them on and you can really barely hear anything from the outside world once those things are on, right? And the way that these headphones work is they have a microphone that picks up sound from the outside world, and then they make a noise with the same wave function, okay, but shifted by 180 degrees, okay? So as it comes in, if this is, say, P, and this is time, it might look like this, right? Because the outside world has a whole bunch of frequencies all getting mashed together, and what you get is this noise, right? This just whole conglomeration of a wide difference of frequencies. And so you get this really complicated wave. You don't get this nice sine wave. What the noise canceling headphones do is they add a wave that, you can see my drawing ability is terrible, but that does the opposite of whatever this thing does, okay? So it comes down. That's as best I can draw it. But it adds this wave in that's the opposite of the sound that it's picking up from the outside world. And what that does is this over here, okay? It's outputting a pressure wave that's just like the one from the outside world, but in a 180 degree shift in phase, okay? And so it adds those together, and what you get is nothing, okay? And so it cancels the sound from the outside world. And this is why they're amazing for canceling some things, but other things they can have a little more difficult time with, right? So, for example, the ones that I have a pretty tough time with sudden, really loud noises, okay? And the reason is, one, the electronics have to be able to react in time to the outside noise in order to cancel it, okay? And to fully cancel it, they have to be able to produce a noise at the same volume, right? Because we said to fully cancel something with this superposition, we had to have the same amplitude, right? And that in the pressure wave sense means that I have to be able to create the same pressure. Well, if something is really, really loud, most headphones can't make that really, really loud noise, right? They're not designed to, because they're right in your ear. Now, the plus side is they only have to make that noise right in your ear, right? The speaker is right next to your ear. And remember, we had our I goes like 1 over R squared, okay? So the really loud thing might be a little further away, and this R squared is going to make it less intense at the ear, and the headphone only has to match the intensity in the ear, and it's right next to your ear, okay? So it can match some pretty good intensities coming from the outside world once it gets this little advantage, right? But still, if something's really, really loud, the headphone might not be able to make a loud enough out-of-phase noise to cancel it, okay? And so sometimes you can hear some things through your noise-canceling headphones, but if you have some, you can put them on and you can see this effect actually works really, really well. And it really is just this simple effect. It's just taking advantage of the principle of superposition and creating a wave that's out of phase of all the noise from the outside world. Okay? Okay, so finally, in our consideration of sound here, let's look at the Doppler effect. And let's consider sound coming from a moving source, okay? So let's say this is the source of sound. And as it moves, it's putting out sound wave. So it puts this out, and it moves a little bit, and puts out a new. Okay, let me try to draw this bigger to try to make the effect more dramatic, okay? So sound wave goes out, it put it out, so it goes out a long ways. And then if we run it back a little bit, it put one out here, and it put one out here, and it put one out here, okay? Now, the drawing is bad. It looks like I drew a hard-boiled egg, but this versus this is what's intended here, okay? So this is a source moving in this direction, okay? And what happens is if I have a certain frequency that I'm putting sound out with, then I have a set amount of time in between each kind of pulse of higher pressure, right? So the frequency is the number of cycles per second, right? Which means that the period is fixed, t equals 1 over the frequency. And this period is the amount of time between each crest, okay, or between each trough. And since that is fixed, when I move through the medium, what happens is the in front of me, the pulses come closer together in space, okay? So the wavelength gets compressed, right? This wavelength is the space in between each of these lines. It gets compressed. And behind me, because I'm moving away, the wavelength gets stretched, okay? So out here, the wavelength is getting stretched, all right? But what happens is, when I change the wavelength, the speed of the wave, remember v, is a property of the medium, right? It's a property of the air. When we were calculating the speed of sound through air, it didn't have anything to do with the source, right? It just had to do with the medium. And since it's a property of the medium, and it equals lambda f, if I stretch or compress lambda, I change the frequency, okay? So when a listener listens to it, the amount of time between each of these is dictated by the speed of sound in air and the length of the wavelength, right? And so what happens is, on this front side over here, these pressure waves come together, or come in faster, right? They come in closer together. And so the frequency goes up, okay? And behind this moving source, where I'm stretching the wavelength by moving as I emit this sound, the frequency goes down, okay? So as I stretch lambda, the frequency goes down, right? So lambda up, f down, right? Or if I compress lambda, then lambda down, so f up, because this v doesn't change, right? If this is a v for some temperature of air, that's just what it is. So if I change one, the other has to change because v doesn't change. And indeed, that's what happens. So if I have a listener just standing here, they get a higher pitch as the thing's coming at them. And then as the thing passes them and moves away, so now at a different time he's back here, now the listener gets a lower pitch as the thing moves away. Okay? This is called the Doppler effect. And you've definitely heard this many, many times, right? If you were to describe the sound of a siren going past you or something like that, this is what you would describe. Or when we say when we're playing with a little kid and we show like a car zipping past the little kid, right? We're playing with some cars and we say, oh, the car zips past, we go, zoom, right? And that sound is what it sounds like when a car goes by, right? The engine noise, the tire noise, or if it's a police car or an ambulance or something like that, that sound, that high pitch to a low pitch, that's what it sounds like, right? And that's because of this Doppler effect. Okay, so when something goes by fast, we get this change in pitch, okay? And in my example here, I've modeled it as the source moving, right? And we often hear it as the source moving. So the police car going by with the siren on, or the ambulance going by with the siren on. But if we think about relative velocities, the same effect happens if the source sits still and we take this listener and run him past like this, okay? So if we move the listener, the same thing happens, because now, as he moves, if these are equally spaced apart, if he's going toward the direction that they're going, he'll hit them one after the other faster, right? Because the difference in velocity between the two is bigger. And then if he's going away, if he's going the same direction, he'll stretch out the time in between the pulses, okay? And get a lower frequency. So we get the same thing if we move the listener or if we move the source. And the important thing here, again with the listener, it was the speed of the listener relative to the speed of sound, right? Relative to the waves traveling through sound. And so when we look at the Doppler effect, we can calculate it, but we have to remember that the speed that we're talking about is relative to the speed of sound in the medium, okay? And their speed is compared to the medium. So we don't get the speed by, say, adding the speed of the source and the listener. We get the speed of the source by comparing it to the speed of the medium, okay? So oftentimes we can consider the air to just kind of be sitting there, and then the speed of the source would just kind of be their speed in a stationary reference frame, okay? But if the air was, had a really high speed wind or something like that, we would have to take the speed of the source or the listener with respect to the medium, okay? So in the example of like the car with the siren, it's the speed of the car relative to the air that it's going through that makes this effect happen, okay? Relative to the medium that the mechanical wave has to travel through. So we can calculate the effect on frequency from the Doppler effect, okay? So if we say FL is the frequency for the listener, that's equal to V plus VL on top and V plus Vs on the bottom times the frequency of the source, okay? So this is the frequency that the listener hears, and this is the frequency that the source is outputting, okay? Now the V here with no subscript, that's the speed of sound. So that's going to depend on the medium that we're moving through, right? Most often for humans, that's air. The sound travels through air. It could be the speed of sound in water, okay? But whatever it is, it's the speed of sound through the medium that these things are in, okay? And then in this formula, in the derivation of it, it's assumed that the positive direction is from the listener to the source. So if I have the listener here and the source here, this is x hat, okay? From the listener to the source. So if the source is moving toward the listener, then this Vs is negative, right? Less than 0. If the source is moving away from the listener, then Vs is positive, okay? By the same token, if the listener is moving toward the source, then VL is positive. And if the listener is moving away from the source, then VL is negative, okay? So it's important to remember what positive and negative mean in this formula, okay? And when we use this formula, we're always assuming that x hat goes from the listener to the source, okay? And as a way to check your answer, if you use this formula for the Doppler effect, we know that if the source and the listener are getting closer together, okay? So say the source is moving past the listener, or the listener is moving past the source, or somehow when this distance between them is shrinking, the frequency should go up, okay? It should be higher than the source frequency. So you can always look at your answer and see that that's true. And by the same token, when they're moving away from each other, the frequency should be lower, okay? So this down here is what you want to picture when you're doing your pluses and minuses. But then when you get your answer, you can always look at your answer and tell immediately if you messed up a plus or minus, because if you mess up the plus and minuses, usually what happens is that your frequency either doesn't go up when it should have or doesn't go down when it should have. Okay? And this formula describes why things like sirens or engine noise or tire noise or whatever has this little high pitch to low pitch effect. Okay? And it's for any sound. There's nothing special. We use cars because they tend to move fast compared to the medium. Okay? And if the speed, you can see if the speed is really low, then the change in frequency is really small, right? And if it's 0, these things fall out and there's no change in frequency, right? And so usually we can't hear the effect if the speed is just going slow. So if I'm walking by you and talking, you probably can't hear a change in the pitch in my voice, right? But cars move pretty fast, right? So when cars go by, we can hear the noise, okay? We can hear the change in pitch. So that's why we use cars. There's nothing special about cars or anything like that. The sound doesn't have to be loud. It's easier to hear the effect if the sound is loud, but it doesn't have to be a loud noise. It helps if it's loud because you can hear it from further away, right? So when it's really loud, you can hear it from further away, and you can hear the high pitch for longer, and you can hear the low pitch for longer, okay? But it doesn't have to be loud. The thing doesn't have to be moving at any certain speed. It's just that for your ear to detect it, for us to process it, we need the frequency change to be kind of a certain size, right? There has to be a certain amount of frequency change for us to be able to detect it, okay? So that's the end of our lecture for today. In the next lecture, we're going to look at a few more properties of sound, but we're going to relate these properties specifically to music.